Hello everyone, this is Roberto Torre. I am a PhD student at the Deutsche Telekom Chair of Communication Networks at TU Dresden. And today we are going to look into the chapter Realizing Mobile Edge Cloud with ComNet's EMO that refers to chapter 15 of our book. So a quick look into the outlook. We will first review what the concept of Mobile Edge Cloud very quickly. Then we will set a practical example, we will identify the problem, and then we will propose a solution. Then we are going to, this is a hands-on session, so we are going to use some coding, and we're going to run the code, and then finally the results we get, and a summary summarizing what we have. So a little bit about Mobile Edge Cloud very quickly. So right now we have this Cloud Run. So the idea is that we have the data center far away from where the users are. There is a very long distance. We have the whole internet. We have the backhaul. We have everything in between. And the problem is that the applications that we are looking into in 5G, like drones or self-driving cars, require high reliable and also low latency communication, so we cannot put this data center at the edge, and that's why we move it at as close as possible to the user. So if possible next to the antennas, or as close as possible. So the idea is that we will reduce the latency because the processing will not be far away, and we can offload the network as well, and we can increase the reliability because there is not so much congestion and so on. If you want to know more about this, you can look into the chapter of Mobile Edge Cloud. We are only going to talk about this, but there is more information in that chapter. So let's go directly to the practical example. The situation that we are going to look in here is we have a client that we can see here here in the lower part of the slide, and this client is going to connect to a Mobile Edge Cloud server. Each Mobile Edge Cloud is inside of it also a network itself, a network with its own servers and switches. And this is what we are exactly writing in here. So this switch 2A is the gateway switch, so where the user connects, and then we have some aggregation switches here in the 3B, okay, that deliver the traffic, and then finally the application or the leaf servers, which is here in 3A. Okay, the idea is that the computation will be done in the servers, and of course the switches will be in charge of direct the traffic. When there is a query from the client, it will be redirected to any of those servers. Then there is another, this 3C. Okay, this is another application that we are going to use to measure the latency in the network inside the Mobile Edge Cloud. So the idea is that our application, this client in one, wants to have the lowest latency possible. So we have 8 different servers, and we want to provide for him the lowest latency possible. Okay. So what kind of assumptions are we going to give? So first of all, there's going to be no denial of service. So even if the servers are almost full or they are very loaded, they will always accept a new connection, a new request. the server workload impacts on the response time, because when there's load, of course, it has to divide the tasks, and sometimes our task may not have the highest priority. So in this case, it will impact on the latency. Then only one instance of the application is going to be deployed inside the server. So despite having 8 possible places where to place our application, we are going to only have one instance. The applications migrated are going to be stateless. That means that the application will have no memory. The input that it computes, it will only matters at the moment that it is being done, not moments before. This is very important, because if we want to migrate a stateless application, we just need to stop it, move it to a different place, and then start it again. However, if the application is stateful and it depends on the states from before, we need to not only migrate the application, but also the state of the application. And this is a more complex scenario. Then we are not going to use a real application or a real industrial application, but just a simple UDP sender receiver, because for our example, it's more than enough. Good. So this is more or less what I was explaining in the topology. So we will have, this is going to be the gateway, as I was saying. These are going to be the aggregation switches, and these are going to be the leaf servers. Okay. This is going to be a probing agent that is going to be sending probing packets to the application servers in order to calculate the latency. So we are going to send a request, but the questions are which physical server will support the request? We have 8 different. How will the traffic be forwarded? Of course, in this case, it's quite easy, because the switches, I mean, there's no other way. If we want to access to one server, we have to go there's only one route. However, sometimes the switches are also interconnected between themselves. So what is going to be, how is going to be the traffic forwarded? It's also an important question. Or which metric will we use? Because, as I said, this time we're going to use latency, but there can be, it could be, for example, throughput, because our user wants throughput, not latency. So, as I was saying, we are going to use the metric, but it's going to be the smallest latency. So, we have different latencies. We have the latency in the network, which will be the latency over the switches. And then we have the latency because of the server workload. Because, as I was saying, if the server has some load in it, and we need to split the time for each task, then our task will take more time to be finished. Then we'll have to analyze, of course, the monitor data to see which one is the one with the lowest latency, and finally choose the optimal server. What would happen if we are not using SDN? Well, if we are not using SDN, what we can use to measure the latency is ARP or ping packets. However, the problem with these packets is that those packets are handled in the kernel. So it will never go to the user space, and we will never see the real server workload of our servers. So it's not really a valid assumption. So what would happen with SDN and NFV? We are going to add a new device, an SDN controller here, that is going to be connected to all of the switches. And we will have this probing agent, as I was saying, that it will be sending probing packets to each of the probing servers. Okay. The idea is that we will have, for the 4 probing servers running, and also the probing packet, and they will be continuously calculating the latency. And then we will have this our real server that it will be connected and talking to the client here down. And this server is going to be migrated through the servers depending on which one has the lowest latency. Okay. We are also going to, we have some link delays and so on for this topology. So this is the table of the delays in milliseconds that we add. This is something that it can be changed, and later in the program I will show you how. Okay. So now the controller algorithm. We have two different types of packets. We have the no SDN and the yes SDN. Okay, so for the no SDN, we have this part. If the type is ARP, then we establish the latency. If the packet is UDP, then what we are going to do is it depends on where it's coming from. If it's coming from the probing agent, so from this node, the packet start here. Okay, so we are just going to flood the packet to all the servers, the probing servers, flood an ARP packet, and that's gonna be it. And record also inside the counter of the controller the timestamp. If the probing packet is coming from the server, then we are going to update the service latency, because we can just you can just subtract the timestamps. Then we have here this message count bigger than 80. That is just that if we are doing this over 80 times, that means that we can search a new host. We are doing this so not that every time that we get a new packet, we just change the host, because that what could happen is that two hosts have more or less the same latency. They are always like this, and we get to a point that we are migrating continuously the server, and that of course is not useful. So what we are doing is we are having some kind of timeout that we wait, so it will be running the host there. Then we will find an optimal host, and if the new is different from the old, then we will remove the flows and add the new float, and also send to the server to change the server, so in the physical server. Good. So now let's start with the hands-on. Let's run it. For this, we will need this CompNet simulator that you can download. Okay. Before I go into here, I just want to show. Okay, this is the CompNet simulator. Here you can download it, and there are this is the instruction on how to install it. I have already installed it in my system, and to make things faster, I already have the background file, everything, and it's everything running. Okay, so I just need to SSH into it. Okay, let's go to here, then the app, and then realizing, what was it? Mobile Edge clouds. Let's come here. I'm gonna do the same here. CompNets app, realizing mobile edge clouds. Good. So this is mainly the first part. Okay. Then what the first thing we're going to do is to build the Docker container. Okay, so let's see if we have it here. This is Python manager. Okay, here. So we run docker build t, which is just the name, and then the file of the Docker file. Good. build. This, if you run it, it will take more time. Okay, it will take maybe 5 minutes, but just for you to know. Then we have go to the second step. Okay, that is this the real manager, the controller. Okay, so with this we just will run it in verbose mode, so we can see more things. We have a log file, and we see where the port where it is listening. So we are just going to run this real manager. Good. Okay. So now our controller is running. And then finally we run the program here of the edge cloud. Good. So we see here in the logs that we are adding the controller and the hosts. Okay. We are also adding the switches, and we are adding the links with these delays that as I said, you can just model the way you want. Then we have started the network, configuring host and so on. Here we are just testing that the pings work, so everyone has contact to the rest of the network. Then we'd add here the Docker containers. Okay, and we start. Here we are already measuring. Okay, here we are already measuring. Then when this is over, I will go to these packets and see how they work. But so far, we have here different flags, UDP and ARP. I don't know if you can read it, but as I said, later we will look into it. We have started the probing agent and the probing servers, the 4 probing servers, because we're only working with 4, not with 8, to make this easier. And this part is the latencies that the system is getting. So here we see, for example, that now there's a new server on server 2. Now we remove the container and we put it on server 1, and then we remove it and put it wherever. So the idea is that we are migrating this from one place to another. Now it's going to be on server 3, depending on the latency. Okay. So that is the idea. If you want to look into the code as well, you can just go here to the app, realizing mobile edge clouds. Okay, and here you have the controller. Okay, most of things, for example, this is just to handle to remove the flows, to add the flow. This is, for example, this protocol that I was saying, what happens if it is ARP, what happens if it is UDP, and so on. Okay, here in controller.py you can edit it, you can change whatever you want to work on the controller. And here in Edge Cloud, this is the Edge Cloud, of course, program. Here you can add Docker hosts, you can add the different, so these are for the hosts, these are for the links. Here you can configure the delay and so on. It's still running. Well, you can see more or less how this changes from server to server depending on the latency. Good, let's continue. So what results do we get? We have different latencies. We have latency, link latency and service latency, because as we were saying, one thing is the latency without the server's workload, and the other thing is the latency with the server workload. And here we can see that it is a huge difference. We can see an average of 261 milliseconds for the server 1, while in the service latency is more than 1 second. It's important to say that this is like an adjusted link latency, because there were some outliers that we just removed. What we did was we took the distribution of the link latency, and we took the standard deviation, which is this one, okay, and so we removed the values that were outliers. So, for example, in the service latency that were less than 1,000 and more than 2,500. What we get here, for example, is we get around 60 to 70% of the packets are inside this standard deviation, which is more or less the percentage of packets that will stay in a normal distribution. So that can let us know that the distribution of this latency is normal. Anyway, so as we were configuring the latency here up, so we saw that, for example, for the server 1 is 100, server 2 is more and more and more. So it makes sense that here also the fourth server takes more time than the first server. Okay. This is a plot with exactly the same values, okay, with standard deviation. We can see the difference between the service latency and the link latency. Then we wanted to know also how reliable this is. So what we did was, over a certain number of packets, we wanted to see the standard deviation in milliseconds and when it gets stable. We saw that more or less up to 10,000 number of 10,000 packets, the standard deviation remains more or less stable. We have here service in server 4 and service in server 1, server latency, and then link latency for the server number 1 and link latency for server number 4. Another thing we observe also is that there are more number of packets for the link latency than for the service latency. We have to think that for the link latency, I mean, this is due to two things. The first one is that before the probing packets are starting, it is UDP packets, the packets are already connecting, and some ARP packets are already sent, and this count already for the number of packets. And also that when there are some periodical ARP packets, queries and so on, that they are also shared, and we are also sending one ARP packet per UDP packet, as you saw in the algorithm of the UDP controller of the SDN controller. So that's why we get this more number of packets. Finally, the latency results observed in the client. So we ran Wireshark in the client to see what's the latency, and we saw that the distribution, the CDF of the latency for each server. So we have server 1, server 2, server 3, and server 4. That makes sense with what we have been studying. So, as a summary, mobile edge computing or mobile edge cloud reduces the network latency by moving the service from the core network to the edge of the network. And we have studied this new situation where a client needs to connect to a MEC server, and he wants it with the least latency possible. And to emulate that and also to study it, we used our CompNet emulator. We created the topology of a MEC server with 4 leaf nodes, and we implemented an algorithm that migrates the service to the server with the lowest latency. Then we ran our experiments, and we got these plots with the latencies. And that's it. Good. Thank you so much for listening.